In this corner, he's powerful without being power hungry. You've seen him all around the globe. He's driving the most powerful motor control designs. It's brushless DC. And in this corner, hold on a second, folks. Late breaking news. All of the other motors have apparently conceded. There you go. Another technical knockout by your favorite and mine, BLDM. Okay. We all know that brushless DC motors are fully in charge these days, without a true competitor in sight. But motor control means a lot more than a motor. It can easily mean a laundry list of components, a bomb out the door, and ultimately a design that isn't really optimized for motor control. Okay, great. Hi, I'm Amelia Dalton, host of Chalk Talk. If we're going to talk about motor control, we need to start paring down that list of components and integrating our power management. My guest is Mark Sosa from Qorvo. In this episode of Chalk Talk, Mark and I are diving into the details of Qorvo's Power Application Controller, or PAC, how it can lower your BOM, trim down your component list, and also give you the memory performance and power management you need. Before we get started, don't forget to click that link. There you can find even more information about Qorvo's Power Application Controller. Hi, Mark. Thank you so much for joining me.
Thank you.
So we're talking about high-performance motor control today. But what particular motors are we talking about that require such high-performance motor control?
Well, it's tough to realize in your day-to-day life, but you are absolutely surrounded by different types of electric-powered motors in your home, in your office, and it's not until you look back and think about all this that you see all of these. In your home, there are, ceiling fans, white goods or kitchen appliances for your dishwasher, washing machine, dryer, refrigerator compressors, tools in your garage such as electric-powered lawn equipment, blowers. In your car, there's a ton of motors, people who have drones, remote control cars, and then, of course, industrial applications like in data centers and telecom and things like that. They are literally everywhere today.
So, Mark, what trends have you been seeing lately in the motor control space?
Well, specifically for electric-powered motors, there's an industry transformation undergoing right now. A lot of motors that were, for example, small gas-powered combustion engine motors are transferring to be electric motors. More and more motors are being introduced in the automobile and the home, and so the growth of the industry is quite large right now. Some of the research firms estimate 11 billion motors per year. This is even harder to believe is that almost half of the electricity provided on the planet is powering an electric-powered motor. That's incredible. And so it stands to reason that if you can make small improvements in efficiency, it will have a large effect. And then there are all kinds of regulatory commissions that are studying this and making sure that from the point of design, we're actually improving the efficiency of motors so that it's not an afterthought. It's fundamental to the design of these new drive systems for electric motors.
Now, I'm not an expert in motors, so can we break down the details? What types of motors are we talking about here?
Okay, so there are various types of motors. Some of these are really quite old technology that go back, decades and decades. Brush DC motors, steppers, and induction motors are quite old and they're reliable. They were easy to drive. That is, that they were easy to turn, but not always the most efficient. In fact, they're, highly inefficient in some of these cases. So even, for example, a brush motor actually has little brushes in there that strike the outside of the motor case, and those need to be maintained over time, and that causes all kinds of problems. There are also brushless DC motors, which are more complex to construct and require more intelligence to control them. However, they eliminate some of the efficiency issues and the maintenance issues that you find in these other motors, and this is the area where the industry is transitioning. There is a penetration that's going from these old type of motors, from brush DC, induction, and stepper motors, towards brushless DC. And as the volumes of these motors come up, the construction cost comes down, and so it's becoming economically viable.
So tell me more about that brushless DC.
Okay, so brushless DC, of course, by the name doesn't have any brushes. So the maintenance issue that you previously would face for brush DC motors, this doesn't exist. They're also higher efficiency, which means things that are really important like longer battery life. Any kind of battery application that has a motor in it, you want it to work when you're using it. Your leaf blower that you're using outside in your yard, you want it to last as long as possible on a single charge. So higher efficiency is really important for these types of motors. The downside of brushless DC motors classically has been that they were a little bit more complex to design and construct. They require electronic control. So you actually need a control element like a PCB in with the motor actually controlling how the motor is, turning and starting and stopping and all this. So these were previously disadvantages, but now that the cost of electronics has fallen over the course of time and the cost to construct these types of motors has fallen, we're seeing this inflection point where it's being able to penetrate these markets were previously unavailable to it.
So what does this really look like today?
Okay, so when we say that a brushless DC motor requires electric control, we're talking about what you see up here on the screen. There are a number of different elements that are required to make the motor go. There's a MCU, which is where a software program runs that actually controls the switching of the power MOSFETs to turn the motor. In order to power that MCU, you need to take the battery supply voltage through a DC to DC converter, which is supplying gate drivers for the MCU, and also a low voltage supply for the MCU, so another LDO is usually in there. On the right-hand side, you see some power MOSFETs, which actually generate the voltage waveforms that go to the motor, and then you need some other components like comparators and amplifiers to sense the current and the voltage from the motor to tell the MCU basically how to control it. So we refer to this as kind of a bag of chips or a bag of parts, as there's many discrete components. And you can imagine what problems that this causes, right? If you're a manufacturer of motors, it's an inventory nightmare. You have to order, these ton of parts. It can cause your reliability to go down because your reliability goes down as a function of the number of different components. So these are easy to construct, but it's hard to differentiate because every one of these components does a very specific thing and it's not particularly optimized for the motor. So high repair rate, trade-offs that you don't want to make for a motor control application, a large BOM, and then with that, of course, there's a large physical size. The circuit board that you need to implement will also be large, and in certain applications that can be problematic.
So how does your Qorvo power application controller family address this type of application?
So the benefit of the PAC family is it allows control of a brushless DC motor through a high performance MCU, which you can get high performance MCUs anywhere, but this has integrated all of the analog electronics that are required to drive the motor. So some of the components that we saw on the slide before here, the DC to DC converter, a high accuracy clock reference, LDOs, gate drivers, comparators, and amplifiers are all integrated into a small, compact IC. Through a single chip, you can actually control and drive these motors, and that enables high performance, higher efficiency, smaller BOM, and cost advantages for these types of motors. So here you see the basic architecture for a battery-powered brushless DC motor or one that's AC-powered like kitchen appliances or ceiling fans. It's basically the same. The big difference is the power coming in is either through AC or lower voltage DC to DC. The PAC family actually integrates all of these power management, MCU, and other analog components for different families of products that can address both battery-powered and AC-powered applications. So compared to a discrete implementation, you can see there's a significant reduction in the number of ICs required for this type of application.
So what kinds of applications are we looking at for the brushless DC?
Well, specifically, the ones that are getting the most attention in the industry right now, we kind of segment into AC-powered applications and battery or DC-powered. AC-powered applications are a lot of the things that you see are in your home, like any appliances, washing machines, dryers, range hood fans, pumps, ceiling fans, hair dryers. Like I said, especially in your kitchen, you have a lot of these you're probably not even aware of. These are applications that are supplied through the AC service in your home or your office, and these are all converting to a brushless DC. Battery-powered applications are actually growing the fastest, and some of these things were classically either unpowered or had a combustion engine, like, for example, lawn and garden tools. Many people still have a gas-powered engine for their garden tools, but more and more people, when they have to get a new one, they're not buying one that's a gas engine, they're getting one that's battery-powered. I have this in my home. Some applications were never powered, but now they are. So the e-bikes, e-scooters, e-skateboards is a new thing from the past few years. If they're everywhere, especially in some other foreign countries, they're extremely popular, right? Toys like drones and remote control vehicles, also popular for battery-powered applications for brushless DC. And then in telecom, there's a huge cooling issue that these data centers have. And so there are a bunch of server and telecom fans that try to take advantage of the efficiency of brushless DC for the data center.
So I would imagine that the consumer and industrial markets would have very different complexity and voltage needs.
Yes. So, for example, we talked about the difference between AC powered equipment and battery powered equipment. So, PAC Family has a portfolio of products that can service both battery powered and AC powered. So on the right hand side here, you see we have a number of 600 volt products. 600 volt products DC are intended to support either 120 or 240 volt AC systems that are powered through your AC electrical service. All the things that we talked about: ceiling fans, washing machines, white goods, even some industrial equipment. But also for lower voltage equipment like power drills, power tools, DC powered fans, we have products that satisfy those as well. Of course, this is not a one size fits all. If you have an AC power equipment, you need a 600 volt power supply and gate driver. If you have a 12 volt drill, you just need a much lower voltage solution. So we have products that run from 48 volts up to 600 volts to satisfy these various battery powered and AC markets. In addition, certain applications are very simple motors and certain applications are complex motors. So a ceiling fan is quite simple, or a compressor that's in your refrigerator, that's quite simple, especially a compressor. It's on or it's off. It only runs at a certain fixed speed. It's very simple. But there are some applications that are quite complex, like, for example, a washing machine. There are various different cycles. It is spinning at a different rate. The acceleration and deceleration is highly controlled. It's interfacing with a system controller. So you require many more computes to support that type of application. And so we also have the segmented according to processing as well, processing and voltage. At the low end, there is a family of devices. We have the PAC52 family. This has an ARM Cortex M0 that's 50 megahertz with 32K of flash. And for these high processing needs applications, we were just talking about, like a washing machine that require much more memory, much more speed. We have a ARM Cortex M4F with floating point that runs at 150 megahertz and has 128K of flash. So between these two processing families and the voltage families that we have, this covers this entire range of brushless DC applications that we just talked about.
So let's talk more about that power application controller. What's all included in that?
Sure. So if you look at what's up here on the screen in front of us, the core of the family is a flash programmable MCU. And like we talked about, we have a low end and a high end. So our low end is a 50 megahertz ARM Cortex M0. Our high end is a 150 megahertz ARM Cortex M4F, and all of the members of the family have a number of shared components for the different applications. So if we kind of walk around the block diagram on the right clockwise, they all have serial interfaces. Like UART is the most popular in motor control because it's got good noise immunity. But sometimes there are SPI and I2C that are required to talk to other peripherals. In highly deterministic applications like in automotive and some other things, CAN is a peripheral that you actually want to be able to do communication to support multiple nodes on a bus in a deterministic fashion. All of these interfaces are available in the family. You always need a PWM engine because this is what's going to be driving the gate drivers, which actually creates the voltages for your motor faces, which is going to drive the motor. So every microcontroller will need to have a PWM engine to run the control algorithm to drive these motors. And in the upper right-hand corner, the power management is really important. You can have 600 volt DC to DC or just a directly connected 20 volt or 12 volt battery. There are a number of different power supplies that run in the pack. but you just supply a single voltage to the PAC and it will create all of these. So what this does is creates all the sub-regulated voltages that the gate drivers, analog, and the digital require, and you can do it without having to purchase external DC to DCs or additional LDOs, and this is what helps reduce that part count. On the middle right-hand side, power drivers. All of our PAC products have integrated high-side and low-side gate drivers. Some of them have open drain drivers for other things like driving relays and things like that. You always need these gate drivers to drive the power MOSFETs, which actually are in the inverter, which make the motor go. The MCU can't drive it by itself with just a 3.3 volt or a 5 volt output. So we integrate the power driver. These can be quite expensive in certain applications, especially for like a 200 volt or a 600 volt output. These are not inexpensive and not small components, and these are all integrated into the PAC family. In the lower right-hand corner, we have a integrated configurable analog front end, which contains some signal processing components like programmable gain amplifiers, both differential and single-ended, comparators, DACs, and a temperature monitor. Again, these are all things that we would have to purchase and put on the PCB as a discrete component, and these are all integrated into the PAC as well. And at the bottom left-hand side, in a control application like this, you are constantly sampling voltage, you're constantly sampling current. So you need a very high-speed autonomous sampling engine. We have a couple great solutions for that, either a 10-bit 1 megasample per second or a 12-bit 2.5 megasample per second ADC. It automatically samples all these signals so that the firmware that you're writing that runs on the MCU to control the motor can provide value-added tasks, not just the basic care and feeding of an ADC. So a lot of this happens autonomously, so the value that you're getting out of the device can be in firmware and providing value in your end product rather than just babysitting other components.
So what does that look like? Do you have a block diagram you can show me?
Sure. So here is an example of a highly simplified block diagram for what the motor controller looks like. This is the PAC5527. So this is a 48-volt brushless DC motor controller and driver. It uses a charge pump architecture for the DC to DC. So if you look in the upper right-hand side, this is the charge pump topology, and this is where your battery supply would come in. And it's a very simple topology to implement on the PCB. There's really only two capacitors, storage and a flying cap. Of course, customers like this because it's highly integrated. They don't have to spend a lot of time designing their circuit board. They don't have to spend a lot of money on different external active and passive components. And the charge pump actually supplies the high side gate driver by creating a 10 or a 12 volt gate drive supply. Just to the top left of that, there's a low side gate drive supply that's also an integrated buck boost controller. So both your high side and low side gate drivers need a supply. We don't want to have to purchase an external DC to DC for these. So these two DC to DCs provide those supplies and they're integrated into the device. On the center and the top, there's an auxiliary 5 volt 25 milliamp system supply. There always seems to be other peripherals on the PCB that you need to power, like possibly potentiometers or maybe driving LEDs and other types of serial communications ICs. So we have an extra 5 volt supply on here so customers can actually just take advantage of this rather than, again, buying an extra LDO or regulator that they need to have on their circuit board. On the right-hand side, in the top middle, these are the gate drivers. They are integrated 48-volt gate drivers. Because this is a charge pump architecture, we don't have any bootstrap components or a bootstrap node on here. So you can see it's being driven just with a high and low side gate driver and a source there. And this can directly power your MOSFET inverter. And just below that, with our integrated differential amplifiers, we can directly sense the voltage across a sense resistor for current or a divided phase voltage for helping control the motor through the algorithms that are running in the MCU, like field-oriented control or back EMF processing. In the lower right-hand side, we have other typical things that you find on microcontrollers. We have 3 USARTs, and those can be configured for either a UART or SPI interface. I2C, CAN, GPIO. There's a number of these different serial interfaces that are available for customers. It all is kind of application dependent on what their board and their system needs. Below that, there's a number of analog inputs that you can sample other signals, such as an external temperature sensor or the battery voltage. And then there's some other interfaces here. QEP is a common high-speed decoding interface that some applications require. And then at the lower right, we have a feature we're going to talk about in a little bit. The PAC has an exceptionally low quiescent current mode we call hibernate mode. And this is really important. And it's important in high voltage because for certain applications like a compressor, your refrigerator is always plugged in, but your compressor is rarely running, right? So the less power that you consume when it's not running, the better the efficiency of the machine will be. And Energy Star and all these guys were imposing all these requirements that are particularly hard to meet, and they're going to continue to be hard to meet. Having really low IQ performance is important for these products. But specifically for the 5527, this is used in power tools. And why do I care about this for power tools? Well, when I'm not using my tool, it's still connected to the battery, and it's going to deplete that battery slowly over the course of time. And many people go every once in a while to pick up that drill, and they kind of expect it's going to work. If you haven't used it for 6 months and you pick it up and the battery's dead, well, that's no good. So having a really low quiescent current can make these things last a long, long time in between battery charges.
So it seems like this PAC could save me a lot of board space. Is that what you guys are seeing?
Yes, definitely. I mean, the biggest benefit PAC is it has the high performance of existing motor control solutions, but it's got this extremely high level of integration, which provides all kinds of system benefits. So up here, you actually see a refrigerator compressor. This was one of our success stories. We have a customer who we helped with this solution, and if you look at their solutions over the course of time, they were large, they were costly, they had a lot of PCB components, and also their standby power was quite high. So if you look over the course of time, solutions A, B, and C, they were able to make improvements, but these are still discrete implementations. When we were able to do this with PAC, we were able to cut the board size in half. The cost of PCB components that due through the integration was also down significantly, but the hibernate mode current, this is the IQ that we were talking about, the quiescent current, substantially better. And again, this enables all kinds of benefits when the application isn't running. So you can see that the benefits of an integrated solution provide, it's an extremely better standby performance. And so these are the kinds of applications where the PAC family excels.
So let's talk more about applications. Where could I use the PAC?
Okay, so one great application for the PAC 5527 is in battery-powered tools. We'll take a drill, for example. A power drill is a really high-power battery-powered drill, but even though it's high power, as the generations of tools are developed, they are mechanically shrinking, right? They're getting smaller and smaller. I remember 20 years ago when I bought or 25 years ago when I bought my first battery-powered drill, it was huge and it was heavy, and now they're getting smaller and smaller, and the punch that the tools have is incredible. The issue is that, like we're talking about with a brushless DC motor, you still need electric control. And the circuit board that has to go into the drill is impossibly small. And it either goes in the handle of the drill or right on the barrel underneath the motor in smaller and smaller spaces. Yet, because of the torque that the drill needs to provide, it's still a really high power application. And so the design that you need, like for any brushless DC, is at a very high level, what you see in the lower right there. You still need a high power inverter connected to the motor. You still need a bunch of gate drivers and an MCU to control the gate drivers, and amplifiers and comparators, and then some LDOs to create different power supplies. So customers are trying to shrink this thing to get it to fit in these smaller design tools and deliver a high power, and it's really hard with brushless DC.
So how does the PAC 5527 compare in here?
So, like we were talking about earlier, all of these main components, the accurate clock reference, the power management, gate drivers, amplifiers, all integrated into the PAC. So there are other passive components that are required in the application, but there's only one IC that's required by the application. And so these are really small ICs. This one here happens to be a 6x6 millimeter QFN, 48 pins. And what this enables you to do is really shrink that PCB size. So in the discrete design, we're down from 7 different ICs to 1 IC. But in addition to that, because of the integration, you also save 2 of the IC savings come from power management that's included into the PAC. There's 10 passive components you no longer need when you move to the PAC design. And the same for gate drivers is 3 additional ICs are included into the PAC device, and there are 18 passive components that you can save by moving to this design. So the savings going to an integrated architecture in an application like this are substantial.
So Mark, what does this really buy me as an engineer?
Okay, so to drill down just one level to look at what we're going to get from a PAC 5527 base solution. So on the first line here, we have integrated MCU and analog, all the analog peripherals that you need to control and drive a motor in this single small IC. And the MCU is high performance. This is a 150 megahertz ARM Cortex M4F. This allows you to implement more differentiating features. It's high performance control. With the extra memory that this solution avails you of, the 128 kilobytes of flash, you can have highly advanced motor control. You can implement features such as in-system flash updates. There are some UL requirements that customers are going to have to satisfy these days, which you have power on self-test diagnostics to make sure the MCU is working, and also they have to run periodically. And these features require memory, and you have this kind of memory and this kind of device to implement this kind of feature. And as far as power management goes, the 48-volt charge pump is integrated. You don't need an external DC to DC. The PCB design is really simple. It's just 2 capacitors. And this also allows you to get to 100% duty cycle for high output applications, which a bootstrap style gate driver can't do. And on the next slide, the total hibernate mode, we also talked about how important the quiescent current is. This device here is about 8 microamps when it's not running. This maximizes shelf life on a single battery charge, so when you go to pick it up months later, you'll still have a good amount of charge in there, and you can use the tool without having to immediately recharge the battery. For the programmable gate drivers, this eliminates 3 ICs. These ICs can sometimes be expensive. They're always large. And also importantly, this is kind of a smart gate driver in that we can do internal slew rate control. And through the fact that it's a charge pump gate driver and we control slew rate internally, this eliminates 18 additional passive components. These are not necessarily expensive components, but they take up a lot of room. And these are the kinds of things that allow us to get in a smaller and smaller form factor circuit board. And then finally, the integrated signal chain. We integrate 3 differential amplifiers and comparators that you need for setting thresholds for overcurrent and overvoltage detection. These are also additional components that are integrated into the device and makes the solution quite compact.
Okay, you said compact. Now, how compact?
Well, here's an example reference for this. So this is a 1 kilowatt board, right, for an 18-volt power tool like a drill. It is impossibly small, 4.5 centimeters by 2.5 centimeters. The single IC that we have on there, the PAC5527, is all you need to drive the power MOSFETs. The power MOSFETs always have to be external because they're so large and they generate a lot of thermal activity. So if you look at the high integration here, this is not a very busy board and it's quite compact. This allows the layout to maximize components that create parasitic resistance. You can have nice big swaths of copper. It can be thermally well behaved, and PAC is just a controller. PAC will be not only the coolest thing on the board, but the least thermally intensive thing on the board. All the power you're going to see is going to be drawn through the power inverter. Well performing, it enables you to have this tiny board at a very high output for up to 1 kilowatt.
Wow, this has been a lot to cover today. Mark, can you recap your main points for me?
Sure. Okay, so what is novel about the PAC family is it is extremely highly integrated. The flash MCU and all of the analog components you need for a brushless DC control and drive is integrated into a single device. The gate drivers, power management, and single chain are all included. These are large components. They are sometimes expensive components, and they are all integrated into the PAC device in a really small form factor QFN package. So this allows you to have high performance control and power management in a single IC, and it enables this really impossibly small footprint we were talking about and BOM reduction. And then also because of the high amount of flash memory and the high frequency of the MCU, you can have very advanced control IP as well. We have solutions across the voltage spectrum for brushless DC motors, for battery-powered tools and DC fans. We have 48-volt solutions for what we call middle voltage, medium voltage applications like garden tools or a little higher voltage, maybe 36 to 80 volts. We have 160 volt DC solutions and industrial fans. And as well, for anything that's AC powered, we have the most products at the 600 volt node for different types of white goods fans and compressors.
Okay, I'm going to click on that link and go to a Mouser.com site for more information. But Mark, what kind of stuff will I find when I get there?
On Mouser, you can look up any of the PAC family. You can look them up by voltage, and it'll show you all the members of the PAC52XX and the 55XX family. From there, you can download some of the collateral like data sheets for the device that describe what it does. For additional detailed information, of course, you can go to Qorvo.com under the programmable power management area, and we have an arsenal of documentation there like user guides and schematic references, Altium files, models, and any kind of information that you need to actually do your design. The firmware and software, Windows GUIs that you need to evaluate these devices as well. Everything you can find out there on Qorvo.com.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Mark. It was a pleasure speaking with you.
My pleasure. Glad to be here.
And before we go, you didn't forget to click that link, did you? There you can find even more information about Qorvo's Power Application Controller. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.